Has everyone signed in? Raise your hand if you have not signed in. Excellent. Let's begin. So, I'm Yu Yang, and I'm here to talk to you today about the real networking stack. And if you look in the bottom right of the slides, yes, I made these slides in a different software. So please excuse if any formatting looks a little bit off. All right. So, I guess first we'll just go over like a basic model of the internet. Oh boy, the text is already getting a little bit wonky. All right, anyways, first we're gonna go over a basic model of the internet. So you have your endpoints, which are the machines that are you interact with every day. So these are your computers, your laptops, your smartphones, tablets, smart fridge, Amazon Alexa, whatever. And these are sitting on the edge of the internet. And then, but also in this category, which sometimes you might not think of it like that, you have servers. I know that it's easy to think of servers as being quote unquote inside the internet, but the core of the internet only really has the routers, and it's the point of that is to keep all of the software that's handling data transfer as simple as possible. So routers, their job is to just get information to where it needs to go. And so servers are also endpoints. And yeah, so I make this distinction because say that your smart fridge needs to send a message to, I don't know, Amazon to say, hey, you're out of milk. So what it's going to do, the fridge is going to send a packet that's addressed towards Amazon's server, and then but it doesn't really know about what happens as soon after it sends it off. It just says, I want this to get to Amazon, and then the packet is just going to go, and then somewhere through this complex interconnected web in the middle, and it's going to get to Amazon, and then Amazon's going to do the same thing. It's going to send a reply back to your smart fridge, but it doesn't know about how the packets are being routed. So there's kind of this, I guess, fog that's going on in the internet where you can only see where you can kind of direct where your packets are going, but you don't really know what path it takes. So the title of this video is the real networking stack. So what is a networking stack? In networking, the protocols that are generally used in networking are kind of arranged into what are known as layers of abstraction. And essentially, you can think of it as wrapping a layer of data in another layer, and that as you go down like the hierarchy, and I'll have a diagram to show this a little bit later on. And the reason we do this is because it's easier to maintain things at, well, there's many things that we require of the internet, and it's easier to maintain these things separately. And I'll go into that a little bit more in the future. And every quote unquote layer plays a different role in ensuring that information gets to its destination. So as an example, if you're a web developer and you're just developing some web app, you really don't want to be worrying about what the Wi-Fi signal strength on the laptop that the person is viewing it on, or if they're even viewing it on a laptop. Maybe they're viewing it on a smartphone and they're connecting over cellular or even satellite now with like Starlink and stuff. The web developer doesn't need to worry about that, and whoever's developing the and I guess the opposite is also kind of true, which is whoever's developing like the Wi-Fi route, the manufacturer of the Wi-Fi router doesn't need to worry about if you're going to send an email through it or if you're going to browse websites or something like that. So when we talk about the networking stack, you might have heard about the OSI model, which is this 7-layer model that's arranged, that's split into nice and neat layers. And there's a lot of text on that model, but I'm not going to go into that because that's not really how the real network works. Instead, real networking follows much more closely, with what is known as the 5-layer TCP/IP model, where you have the application, the transport, internet, link, and physical layer. And I'll kind of go into what each of those entail. So yeah, we'll start with this model as a baseline and see where we go from there. So earlier I alluded to this concept of a layer. So I guess I'll talk a little bit more about what that is. So you can think of every layer, starting from top, which is application in that diagram below, to down to the physical layer. Each layer is just adding another more information to the beginning of the information in the last layer. So you're just putting a header on it, and well, I have an asterisk on the slide, and you'll see why I put the asterisk there as we move on. But you can kind of, for now, you can kind of think of a layer as everything in the layer above plus things in the layer below. And I have a sample, I guess, kind of packet there. It's not to scale. The sizes of the layers are definitely not like this. But if you were to send a web request, you'll have your application data, which is the technologies that are required for the web request to happen, which are HTML and HTTP, as kind of the innermost layer. And then on top of that, it's kind of wrapped inside TCP, which is a lower level protocol. And then after that, you have IP and then Ethernet. Yeah, if you know me well, you'll notice that I put IPv6 there, and that's for a reason. I'll get into that a little bit later. All right, let's start from the top and move our way down this hierarchy of layers. So at the very top, you have the application layer. This is where application data is sent. So this is going to be your email, your web traffic, DNS, which is something used to map names like ufl.edu to like where the computer needs to send that packet to, or an IP address. And yeah, if you're not programming like lower level things in the kernel or in the hardware, you're probably gonna deal with networking at this layer. And yeah, just some examples of protocols here: FTP, HTTP, DNS. Also, email protocols are also at this layer. Basically, every application, everything you use on the internet at a daily basis starts here and kind of moves its way down. So the next layer in this model is the transport layer. And what this does, the job of this layer is to direct data to the correct application on a machine. So when you have a server, you might be running multiple things on it. You might, for example, you might be running SSH, which is a protocol that's used for remote access. You might be running a web server, which is HTTP. You might be running email on there. And the job of the transport layer is to get your email information to the email server that's running on the machine, and get the web information. So if you're having a website and you need to send some information back, it gets that data to where it needs to go, the web server. And this is where the concept of ports kind of come in. So you might have heard that HTTP runs on port 80. SSH runs on port 22. These ports, it's happening at the transport layer. And this is where kind of data that's destined for a machine is separated out to all of the different applications that are running on it. There's also some other features at this layer. There's data integrity. It makes sure that the data is getting there in one piece. And optionally, if you want, there's data reliability that's ensured at this layer. And two examples of protocols at this layer are TCP, the transmission control protocol, and UDP, the user datagram protocol. So moving on down again from the transport layer, we have the internet layer. The job of this layer is to get packets to where they need to go. So if you want to send a packet to, say, ufl.edu, you're probably not, well, I guess you're on campus, so it's not a good idea. If you want to send a packet to, let's say, google.com, you're probably not located in the same physical location as google.com. So you're going to send your data to your closest router, and then that router is going to send your data on to another router, and you're going to take a series of paths that you're not really sure about to your destination. And the job of the internet layer is to get the information that you want to send to where it needs to go. And so, like I said, it's meant for one of its jobs is for routing between networks, but also forwarding within networks. So even let's say you're connected to like a Wi-Fi router and at UF, and you want to send a request to some other machine at UF. Maybe you're trying to fetch the web page of like a class web page, for example. That's also what's happening. It doesn't have to be between networks. And two examples of protocols at this layer are IPv4 and IPv6. Next, moving on down a little bit more, we're going to get into the link layer. This is where the software integrates with the hardware. Oh, was that a question over there? Or, all right. Next, we're going to move on into the link layer, which is where the hardware interacts with the software. And this is where the concept of a MAC address, which you might have heard of, comes into play. And essentially, this is everyone who's on the same. I guess you can kind of think of it as everyone that's connected to the same Wi-Fi router, or everyone that's on like the same Ethernet link, which is I guess back in the old days of networking, you used to connect the Ethernet cables directly. So I guess an Ethernet cable wouldn't have like two ends, but there was like splitters that you could get to split it up into multiple ends. Although that's not really used much anymore, and it handles what is called multiple access, which means that multiple people can use some form of communication at a time. And I think the best example of this is radio waves. So you're using Wi-Fi, but so is like literally everyone else is in this room. And the job of software at the link layer is to make sure that everyone has like kind of fair access to the Wi-Fi and everyone can get the information that they want to go through. And also packet switching, which is not to be confused with routing, but it's just getting information to where it is on the same link. And error correction also happens at this layer. And two examples of protocols here are Ethernet, which I mentioned before, and 802.11x, which is just, you can think of it as just Wi-Fi. And at the very bottom, we have the physical layer. I personally don't know much about this, but that's why we have the electrical engineers. So anyone in here an electrical engineer? Great. That's what we pay them to do. This physically gets the bits to where they need to go. And so this is kind of like even lower than Ethernet. Usually you think of like an Ethernet cable, and inside there, it's literally like copper wires, which is what twisted pair is. And also like wireless transmission, which is transmission through the air. And something interesting that I found while researching this presentation is you can literally have anything you want at the physical layer. So a while back in 1995, okay, I guess I should go into a little bit more of the history. So there's IETF is like an organization that makes standards for everyone on the internet. And every April 1st, they put out like some type of funny, humorous standard that's not meant to be official, but it's kind of like as a joke. So back in like 1995 or 1996, they made this standard where they recommended that you could transmit internet packets using carrier pigeons. And technically, it's doable because you can have literally anything at the lower layers. That's kind of why we have the concept of layers. You can have any medium you want on the lower layers without affecting what information's at the upper layers. So anyways, so they implemented it kind of as a joke, and not much more was thought about it. But later, in 2001 or 2002, I think a group of people in either Netherlands or the Belgium, I can't quite remember for sure, but they decided to actually implement this, and they sent out 9 carrier. They strapped packets of information, like basically, I guess Ethernet packets, to like 9 different carrier pigeons, like on pieces of paper, and they like sent them off to where they were meant to go. And this is the results of that. Oh, they were ping packets, if you know where that was. But the important thing is 4 out of 9 packets got through. It was a great experiment with insanely high latency, as you might be able to see on the screen. I think 2 of the packets were lost because the papers fell off of the pigeons, so they weren't fastened securely. And 3 of the packets were lost because the pigeons got distracted by another flock of pigeons, allegedly. But this is just a funny story that I found while I was researching this. So I guess now we'll go a little bit into some complications of this model. So before we had this nice neat 5-layered model of the internet, but that's not really how real life works, unfortunately. So the first thing is that the link layer protocol that you use and the physical layer, it's not as flexible as you want it. So specific link layer protocols are very strongly associated with other physical layer protocols. So just a few example, Wi-Fi, it's actually like partially like a software protocol that's implemented on your devices, but it only really works through like the medium of like radio waves, because it makes sense. Like if you if you want to send Wi-Fi over a wire, you wouldn't bother with a bunch of the complications that are there. And the same thing for Ethernet. You can't really send that over the air because it's not quite reliable enough, or it doesn't quite have enough like error correction going on to be able to be sent over the air. And the same thing happens with Bluetooth that also is primarily sent over an air, and USB, which we usually don't think of USB as a network, but it really is a type of what's known as like a personal area network, and it has the same principles. Although instead of this 5-layered model, it's only 2 layers. It's only the link and the physical layer. But I guess that it's not part of like the internet, so a little bit out of scope for this talk. So yeah, let's merge the link and physical layers. But surely there's not going to be any more complications than this. Unfortunately, there are a few issues. And the first one I'm going to discuss 3 today, but the first one I'm going to go into is security. So the internet was designed back when dinosaurs roamed the earth. No, I'm just kidding. But it was designed in as kind of like a side project of DARPA, which I think works with the U.S. Department of Defense. Someone correct me if I'm wrong. But it used to be like this experimental thing, which only like people with like security clearances could access. So there was not really much reason to build security into these early internet protocols. But eventually, the internet became open up to like more and more people, and security started being a thing. But like all of these different protocols, like DNS, FTP, HTTP, IMAP, POP, and SMTP were all meant to send, or all designed to send emails, but they all didn't have any security built into them. So we needed some way of securing these protocols, and we needed to put that somewhere. So in the 1990s, TLS, or transport layer security, was developed to solve this. And now, I guess when you hear the name, you might think, well, it's transport layer security, so it must be in the transport layer. Actually, that's not quite true. Because of some issues that I'll discuss later on, TLS, by the time it was being developed, certain things had happened in the internet where it could not actually be put into the transport layer. So where it actually sits in this model is it sits just above the transport layer. So let's put that as part of the diagram. Although it's kind of an optional layer because you can still have these protocols as they were originally designed without any security, but we'll have that extra layer of security there. And I guess just to give you a basic example of a basic explanation of what TLS is, essentially what you need to know, it adds a little bit of overhead, but in exchange for that little bit of overhead, you get like really good security as long as it's configured correctly, which it often is not, unfortunately. But you get good security, and then protocols that run over TLS usually have an S appended to the end of their name. So we have HTTP. HTTP turns into HTTPS. FTP turns into FTPS. SMTP turns into SMTPS, and DNS turns into DOT because they like to follow patterns. Well, DOT stands for DNS over TLS. I guess DNSS didn't sound as good or something. But as you can see in this model, I previously had like a packet with like TCP and HTTP like right next to each other, and now you can essentially what you can think of it as is TLS kind of goes in the middle of that. And the big benefit of this is everything after the TLS. So all of your application data, everything sitting above the TLS layer is encrypted and secure. You have a question? Yes, DNSSEC signs a DNS request. It does not encrypt them. Yes? Yes, it's DNS at an even higher level. So if you look on this diagram, I have HTML web page after HTTP, but for DNS over HTTPS, it's basically putting DNS in place of that HTML web page at a high level. That's kind of what it is. Whereas if you had DNS over TLS, you don't have to have that HTTP overhead. So it would go from TLS directly. What's directly under TLS is DNS. But yeah, there's quite a bit of competing standards as to how to properly secure DNS. I guess now let's get into problem number 2, which is protocol ossification. When I first read about this, I thought ossification was just like a really fun word to say. So ossification. I just have to say one more time. Anyways, this is the decrease in flexibility caused by people who, for better or for worse, didn't quite implement the standards all the way up to where they were. And surprisingly, this is only a problem when above the internet layer. So below the internet layer, hardware manufacturers have been pretty compliant with the standards put out, and it doesn't really happen. You can really send internet over a wide variety of mediums, but above the internet layer, there's some issues that happen in the internet that prevent this from that that kind of result in a decrease of flexibility. So I'm going to go into a few examples of this. The first example is what I alluded to before. There's protocols in the transport layer, or actually, before you heard me mention that TCP and UDP were protocols in the transport layer, and you might be wondering, well, if there's so many like other protocols at like the application layer, like I listed off, I think at least like 6 of them, why are there only 2 of them at the transport layer? And I guess the answer to why we don't see that more is because for all intents and purposes, only TCP and UDP can be reliably sent over the open internet. They did an experiment of this back in, I think, around 2008 to try to see if other protocols could be sent, other transport layer protocols. So it's where you see that TCP and UDP in this graph, right above the internet layer. How many of these protocols could be sent over the internet? And they found that in less than 30% of cases, other known protocols, so other protocols that were well defined and known at the time, were able to be sent, and less than 10% of in less than 10% of cases were like arbitrary protocols allowed. So like if you just decided to design your own, I don't know, super TCP, it would only be passed in less than 10% of cases, and that's not really like a reliable way to send information over the internet. So now you might be wondering, well, TCP and UDP are so great. Why do I need other protocols? I guess to answer that, I'll get into a little bit into TCP and UDP. So TCP, the primary benefit of that is it makes things really easy on the application developers. Essentially, all you do is kind of dump data into a pipe at one end, and it'll come out in the correct order on the other end, and intact. And that's like a really, really nice thing to have. Whereas that doesn't really exist for the other protocol in use, which is UDP. And TCP is also, I guess I mentioned it, but it's in order and reliable. And it also has built-in congestion control, which means that if you detect, or if TCP detects that there's some congestion on the network, it'll back off and kind of be like a good citizen for the network. And whereas UDP doesn't do that, I've had this analogy told to me by someone else. I can't quite remember who they were, so unfortunately I can't attribute them. But they said that UDP is kind of like a fire hose of data. So if you're sending UDP at them, it's kind of like a I guess you start a conversation, but you just start like yelling nonstop at their face and hoping that they can get as much of that information as possible. Whereas TCP is like having a polite conversation, and and a benefit. Another feature that neither TCP nor UDP have is something known as multipath failover. So if you're on your phone, for instance, and maybe you're on like maybe you're downloading like a large file on your phone. If for whatever reason your Wi-Fi drops out and your phone like automatically switches to like your cellular network, more than likely your download will either fail and you have to start it all over again, or it'll automatically pause, and well, it'll be annoying because you have to go in and like restart it. But if there were multipath failover in the transport layer, this wouldn't be an issue. You could you could be on like an unreliable Wi-Fi network, start downloading like a big file, and when I guess if the Wi-Fi network should go out for whatever reason, it'll seamlessly switch to your cellular network connection, and both your browser and like whatever web server that you were talking to will just continue the download like nothing nothing happened. It'll just like seamlessly continue. And this is a really nice feature to have that isn't in any transport layer protocols. That isn't in either TCP or UDP today. And finally, there's a security weakness in TCP where there's this attack known as SYN flooding, where you can perform like a denial of service, or you can make a server really slow or unresponsive by sending a bunch of SYN packets, which just know that it's an attack that exists. But with some innovation in transport layer protocols, a lot of these problems can be fixed. Sometimes, I guess the main benefit of UDP is that it's a lot faster than TCP, and sometimes you really need that speed over like reliability, but you don't want to give up other nice things like congestion control. Because if you're congesting up the whole network, link, not only is it going to be slow for other people, it's probably also going to be slow for you. So there's other protocols that seek to resolve this. And also there's other protocols which have this nice feature that I just talked about, the multipath failover, where you can change networks. You can kind of like hot swap networks without affecting like ongoing connections, which is you can think it would be a really, really nice feature to have if you have like some mission critical server that needs to stay connected at all times. And also these other protocols have like inbuilt protections against the SYN flooding attack, while TCP, you need some external mitigations that aren't quite perfect. So yeah, there's some mitigation that's been stifled in the transport layer. And I guess another consequence of this is because TLS wasn't able to be integrated at the transport layer, which I mentioned a little further back. There's a lot of overhead, 6 to 8 round trip, or sorry, 3 to 4 round trips, in fact, of overhead every time you need to make a secure connection over the web. And again, that's not very performant. It's not ideal, especially if you're located really far away from the web server. Let's say you're here and you need to talk to a web server in like, I don't know, Germany. It's gonna have to, the bits, no matter how responsive the routers are, the bits are still gonna have to physically travel from here to Germany, and that's gonna take like 500 microseconds maybe, which for 3 or 4 round trips, that means up to 2-second delay if you're using TLS. Although I guess it's usually not that extreme, but I'm making the numbers a little bit more to make it seem a little more noticeable. But for mission critical applications, you might see how it's less acceptable that you have this type of additional delay in the connection. So what they did, they developed like a workaround to kind of solve this issue using Quick, which is it stands for, I think, Quick UDP Internet Connections. It's another one of those fancy recursive algorithms that people like to use for whatever reason. And what it does, it allows you to talk securely, but with less overhead. It does the same in two packets or 1 to 2 round trips. But because, as we said before, you can't integrate new information into the transport layer, Quick had to be laid on top of UDP. So there's still additional overhead in the size of the information being sent. There's like kind of wasted information being sent like all the time, which is the UDP header. If you remember back to what I said a while before, every single layer is adding another chunk of information to the beginning of the packet. So if Quick is sitting on top of UDP, that means that all the information associated with UDP has to be sent with every Quick request, even though it doesn't really need to send all of that. So this is an inefficiency due to how TCP and UDP are the only protocols that can really effectively be used over the internet. And I have another example of this loss of flexibility. So for the longest, and this is kind of going back to TLS. So for the longest time, TLS 1.2 was the version of TLS that was in use on the internet. And like router manufacturers and firewall manufacturers, I guess kind of in the name of security, decided to mark all like invalid TLS version numbers as suspicious, and like maybe like block them or whatever, because I guess maybe in like 2014 some router manufacturer said, hey, there's never going to be a TLS 1.3. TLS 1.2 is perfect. So they kind of like marked TLS 1.3 packets as suspicious and wouldn't like let them through, and this got like widely deployed over the internet. So I guess later on in around like 2016 17, we realized, hey, there's actually some issues in TLS 1.2. So we'd like to make a new version of TLS. And what happened was, unfortunately, when they started running tests with this new version of TLS, they realized that all of the packets weren't being passed through because way back, like a few years ago, the router manufacturers and like decided that, well, TLS 1.3 is clearly suspicious since it hasn't been released yet. Well, like since it doesn't exist. So so all of the TLS 1.3 packets were blocked. So what they had to end up doing was for all TLS 1.3 traffic, it's spoofed as TLS 1.2. So in the version field of TLS, it says, "Hi, I would like to talk to you with TLS 1.2." And what a standards compliant server will do is um, it'll send back a response with a little bit of extra information that says, "Hey, are you actually using TLS 1.3?" And then the client will send back, "Yes, I'm actually using TLS 1.3," and they can continue with the TLS connection there. But this was a I guess a ridiculous example of what happens when a lot of people don't follow like the standards that were originally outlined. And this has actually been defined into the RFC, which is like the standard for the internet. Um, they renamed the version field to legacy version, and it says that for all future versions of TLS, all of them will be marked the same as it is for TLS 1.2 because of this issue. Question. Yeah, for as long as yep, it'll be there for forever. um, but yep. So this is a great example of things that kind of go wrong when people make assumptions that shouldn't be made. Like maybe they realize, I guess maybe in the name of security, maybe way back in 2008, um, or like 2010, it was suspicious to have this packet, but they weren't as forward thinking. So they thought, well, we're never going to have a TLS. We're never going to have the next TLS version up. And yep, this happened. Um, what time is it? Okay, I guess I'm running a little low on time, so I'm gonna go through these last few examples a bit more quickly. But another example of things getting stuck, kind of like the TLS version, is the user agent. So the user agent is something in your browser that your browser sends to identify itself to websites. And way back in the old days, they used to be a very simple in the format: your browser's name, your browser's version, and maybe some extra info about that the website might like to know, like your operating system or like what type of architecture you're running or just like basic information like that. But back during the browser wars, which is a very fanciful name for when Microsoft tried to monopolize like the browser market with Internet Explorer, they Netscape, which was kind of like the precursor to Mozilla, they wanted everyone to use their browser. So what they did, they released the feature in their browser, which is using frames. So this is kind of like you get to embed other things into your website, like maybe you embed like a Facebook post or like a Twitter post into your website. And basically, you can kind of think of them like fancy versions of websites. And so Netscape was kind of first in the game, and they released their browser with this new feature where you could have fancy websites. And then they started getting more market share. So all of the other browser manufacturers said, "Hey, we need to catch up and also do this." So maybe like a few years later, all of the other browsers caught up with this. They also implemented the same thing that Netscape did, and this was back in the time before there was like standardization on the web. So every web browser would render like a different version of the website, which is annoying. Luckily that doesn't happen much today. So what a lot of website owners did, they started detecting if the browser was Netscape, and if it was, it'd serve them like a nice, fancy, nice version of the website. And if it wasn't, it would serve them like this plain version of the website with like only text on it. Maybe if you go to like some really old website on the Internet Archive, you can see websites that look like that. Um, but so yeah, when everyone else finally got around to implementing these fancy website features, when the browsers identified themselves as their browsers, they were only getting back plain text versions of the website. So what ended up happening was everyone decided to spoof their browser's name as Netscape. So everyone's browsers contains everyone's browsers kind of identifies itself as websites as Netscape version 5.0. And that has persisted until today. If you go to useragentstring.com or whatever your favorite way to check your browser's user agent is, you'll see that your browser's user agent, more likely than not, contains Mozilla 5.0, because way back when this story happened, and now this will forever be part of how your browser identifies itself to websites. So I guess everyone's using a Netscape browser in a way. Yeah, and mind you, this was like what? Okay, it's 2025. This was like 30 years ago, and we're still stuck with this. But yeah. All right. So I'm going to discuss one last problem before we with this networking model. before we wrap things up. So when networking was first developed, like I alluded to, it was developed like as this side project of like the U.S. government, and they they thought that there was not really much reason to have like a lot of unique websites on the internet. So I guess I should go a little bit more into what an IP address is. An IP address is a it's kind of like a unique identifier for your computer that's kind of unique across the entire network. So if you say I want to go to net IP address 10.0.1.5 or some address, maybe that's not a good example. If I say I want to go to the IP address 8.8.8.8, you know that that address is going to be associated with exactly one computer on the website on the internet, and when you send the packet out, it'll get to that computer. And way back when, they came up with a scheme that allowed for a little over 4 billion addresses, and that was more than enough for what was all the way back in those days when the internet was this private thing of the U.S. government. But as you might have noticed, 4 billion is just over, or maybe under. I don't know how much the world population is, but it's just around that half of the world population mark. And since everyone probably has more than one device, like you probably have a laptop and a phone, maybe a desktop at home. That's clearly not enough addresses for everyone. However, they did anticipate this problem in the 1980s. And the IETF, the organization for like making standards on the internet, quickly took action and proposed and ratified IPv6, the new version of the internet protocol, with a lot more addresses in 1995. And I guess the commonly cited statistics for this is there's more than enough addresses for every grain of sand on Earth. So it'll last us for the foreseeable future. So yeah, luckily, IPv6 was developed, and now we're all using it, and we don't have to worry about this problem any longer. Just kidding. And so, unfortunately, IPv6 was expensive and difficult to deploy, and many people didn't really have many internet providers at the time, and even now, didn't really have like a financial incentive to make the switch. So we were stuck on the crusty old system from the 1980s, and eventually, 15 years after they developed IPv6 to solve the problem of the unique addresses for every computer on the internet running out, the addresses ran out, just like they predicted back in the 80s. And unfortunately, because the IETF, like the standards board, realized that it was pointless to try to get people to stop using this legacy version of the internet protocol, they just they gave up. They like disbanded their working group to try to get people to stop using IPv4 in 2018, which is like, man, that's like 7 years ago at this point. So we had to do something because we clearly don't have enough internet addresses for everyone. And the solution for that is network address translation, or NAT. And if I sound a little bit exasperated right now, it's because I've worked with this technology before, and it is the worst for like network engineers. What you need to know about it is it rewrites public IP addresses. So every computer actually has two IP addresses. You're going to have a private IP address, which is unique within your local network. And you're also going to have a public IP address, which is unique across the entire internet, but it's not unique to your computer. It's unique to your network. You can actually check both of those addresses. If you go to some IP tester website on the internet, or just type in what is my IP into like Google, you'll be able to see your public address. But if you check, like if you go to your phone's or your computer's internet settings and check what IP address you have there, more likely than not, in like 99% of cases, it's not going to match what you see on that public website. And that's kind of like the difference between your public and your private IP address. So yeah, if you go to your computer settings, you'll see like an IP address that starts with like either 10 dot something or 192 dot something or 172 dot something. But that address is not unique. So if, let's say at UF, we have a mail server on 10.0.1.5, if we go to some other network, like maybe we go to, I don't know, UCF's network, they might have like the president's computer at that address, because these are not unique addresses. And that's why we need to kind of like transfer them to like different unique public facing addresses. And I guess this works because there's not 4 billion different internet providers in the world. At least I hope not. Like having to deal with like Cox is enough for me. But so um, so this works, but it's kind of like a band-aid on the problem, as there will inevitably be more devices that are connected to the internet. And so there's a common argument in that many people make, which is that since my computer doesn't have a publicly routable address, clearly this setup is more secure than if every computer had a publicly routable address. And unfortunately, there's ways to configure this network address translation in an insecure way, just like there's ways to configure traditional security tools in an insecure way. And just having this layer of network address translation isn't really any better than just having like a firewall that like drops all packets by default. And people will have long discussions with me about this, and I'd be more than happy to have these discussions with you after this talk. But yes. Well, not necessarily, because you could also have a firewall on the router, and the router that's upstream from you could block all the traffic that comes into the network as a whole. Um, yeah, yeah, that's true. That's another problem with NAT. If you have too many devices behind the same addresses, well, if you have 64,000 active connections, it won't work. Really? Well, no, but like the external one, eh, it's complicated. It works, but like now you're breaking more like peer-to-peer traffic. Well, we'll talk to that later on. But yes, that's true. A while back, or if we decided to switch to IPv6, if you wanted to set up like a Minecraft server and open it up for everyone to play on, you wouldn't have to pay anyone to do it. Like now, I think you have to pay like Microsoft some money to like set up like a Minecraft Realms or whatever it's called. But yeah, you would be able to do it right at home if we had IPv6, and you could like just set up a server. So yeah, I'm gonna discover a few issues with that. I guess the first issue is it can give some network administrators a false sense of security. So like it's easy to think surely if my addresses aren't like reachable from the public internet, bad stuff can't get in, right? And there's interesting ways to like I guess not really circumvent in a way because every network has an NAT, but there's interesting ways to make connections to internal computers despite NAT. You can look into them a little bit more if you want to. I think I'm running out of time to talk directly about them, but there's reverse shells and NAT hole punching, which is like a really creative way to get around NAT and what like software like Skype uses for legitimate purposes to try to get a direct connection going on between you and someone else. And also another issue with NAT is that it's a really easy single point of failure in a network. Um, and that's because if you want like um, if you want people to be able to talk back to you, you need to have like one address and like one port on the internet. And if you have multiple different places where the network address translation is taking place, it's very, very difficult to arrange that unless you have like super intricate networking knowledge. And definitely not something that you could like just plug and play like a router at home. So for the vast majority of networks, they're gonna have one box that does this network address translation. And this is like a single point of failure, which is generally not good to have because someone could just focus their efforts on that box to try to like take it down. And finally, like I briefly alluded to before, it breaks the peer-to-peer architecture. So I guess you can't just like host a server on your own network. You have to like get you have to either like have a bit of networking knowledge to be able to open up ports, or you have to like pay someone to like with like public IP addresses to do it for you. And I guess the last issue that I'm going to talk about today with NAT is that it this is like a from a network engineering perspective, it forces routers, which are generally um, which are generally only meant to go up to a certain layer in the in the internet model. So this nice, neat layered model, which as we went through the presentation, we saw progressively get less and less neat. It blurs those boundaries between the layers even further by forcing routers to modify packets at a layer higher than they're supposed to interact with. And this makes it difficult to optimize things at the internet layer because, I guess not quite every router, but a lot of routers now have to worry about like this higher level thing, this transport layer. Because remember, NAT, what it does is it tries to put multiple devices behind a single IP address. So you have to have something more than just the IP address to identify your machine. So you have to muck about with like a little bit higher level things. And also, it tends to obscure the true source and destination of packets. So you can only identify like the source of of like say a malicious packet down to the network level, not like to the device level. And you might say, well, this is fine. It doesn't really matter. But like for example, let's say that someone on that's on the same network as you decided to nmap Google. Don't do that, by the way. Don't run security tools on like computers that you were not authorized to run security tools on. But let's say somebody decided to like launch an attack from Google against Google to from your network. Well, Google would probably take defensive action to try to protect their networks, and a really easy action for them to take is to block your address. Unfortunately, since that address doesn't belong to you, it's like your network's address. Everyone on the network now isn't able to reach Google or whatever service that you needed to reach, and that's kind of an issue that wouldn't be that wouldn't be that would be resolved if every computer had its own address. Okay, and finally, this having NAT here kind of violates the end-to-end principle. Like I said at like the very beginning, the general idea of the internet for the longest time was to keep all of the complexity out of the core of the internet, the routers where everything's being forwarded, and all of the complexity should be in the endpoints. So your computer kind of has a little bit of has a has like your computer has like jobs that it needs to fulfill. Like it basically all of the changing of things between the different layers of the model. I guess besides the internet layer, the vast majority of that happens at on either your computer or like the server. But with NAT, it forces boxes in the middle to kind of mess with more things than what's at the internet layer, which I guess it doesn't affect the average person much, but like network engineers don't really like that. So I guess today we talked about the real networking stack, right? In conclusion, this is what the networking stack looks like. Not really. There were a few things that I didn't go over because otherwise this presentation would be 3 hours long and nobody would be here. But there's things that don't quite fit into this traditional model of layers, and we can either have a discussion after this or you can kind of research on your own. So like ARP and NDP, those are used on a network for the router to kind of determine what lower level addresses, the link layer addresses, the MAC addresses are associated with what IP addresses. I didn't really address that. Also, there's DHCP, which is when you log on to a network, how do you know what address that you're going to use? That assigns it, but that doesn't really fit neatly into any of the layers defined here. And there's also other protocols that I didn't quite go into because they're not like neatly segmented into these layers. They're kind of like, they kind of live across layers. So yeah, that's talk. Anyone have any questions? Oh, yes. Um, yeah, we're seeing more we're seeing more rollout of Quick for sure. There's like I think well if your browser supports it, which I think it's being worked on, like it'll slowly be supported in more browsers, but if your browser supports it, I think Google and probably other websites, but I can't think of any off the top of my head. But they are trying to support Quick more and more, and it'll speed up your web traffic by just a hair, but maybe it'll probably ease the load up on their servers a little bit. And other emerging network standards, let me think. Hmm. Well, I'm really hoping the other protocols that I mentioned here get implemented, but I don't think that's gonna happen anytime soon. It's like there's I guess the reason for like this limited flexibility in the transport layer, it started in like the name of security. So people blocked protocols that they didn't know about because they're like, well, I don't know about these protocols. I don't know what they're gonna do to my network. But it just decreases flexibility a little bit. Anyone else? Online questions? Okay. Yes. Not necessarily, because your machine here is not going to have an IPv6 address because UF does not have IPv6 addresses. Or I guess UF's networking infrastructure does not currently handle any IPv6 things. Sometimes that's done in the name of security because, I mean, why would I secure one network when I can secure two? But like, um, I guess, oh, sorry, go ahead. Yes. All if you had IPv6 addresses on both ends of your connection, like if your like internet service provider supports that, then more likely than not it'll work. However, you might not be able to get away with not configuring anything on your router because most routers that are sold nowadays have default firewall rules that prevent unauthorized traffic from getting in your network, which is what I kind of mentioned before as to the way to secure IPv6, even though every host is technically internet routable. Uh, did someone have a question back there? No? All right. All right. Well, thank you, everyone. I guess if you haven't signed in already, please make sure to do that. And here are all of our social media links for UFSIT.